Sure. Yeah.
Hey guys, so a quick little segment before the podcast starts. Unfortunately, there was quite a large technical glitch that occurred for quite a long time, for around 20 minutes in the first part of the episode. So yeah, the audio is not going to sound very good, so we apologize for that. Video and everything is okay, but we're just letting you guys know that the audio was not perfect.
Well, it's after like 16 minutes.
Yeah, so I mean, it's good for a long time, and then it's going to be really bad, and then it's going to get back to normal. So have fun. Enjoy.
It's the language of the universe.
But I don't understand it.
Hello, everybody, and welcome back to another episode of the Math and Physics Podcast. I'm your host, Parker.
And I'm Ray, and we welcome you back to episode number 90, where today...
Is it 90?
Yeah.
Damn. That's a lot.
Episode number 90, just 10 for the big 100, where today we actually have a special episode planned, or special 2 episodes planned for anyone that caught our live stream. But today we're talking about the history of physics, and this time we're actually going to be talking about 4 individuals who are all closely knit together, who are all related in some way, all in the same time period, doing relatively the same things. And we're going to make it kind of a 2-parter. So we have a 2-parter history of physics for the very first time on our podcast. I mean, there's going to be a lot of firsts, obviously, but this is one of the first that we're going to try out because, unfortunately, as you might know, an episode did not drop last week. And that is simply because this was the last week before our finals. So, all of our assignments, everything kind of culminated onto this 1 week where we had everything due. So it was kind of hard to do it. So here we are kind of compensating for that fact. And therefore, there are going to be 2 episodes released this week. So if you happen to catch this one on Monday, wait for Wednesday.
Yeah, I think we're going to drop it Wednesday.
Wednesday, the next one will be out. We're going to be basically sitting down here recording the 2-parter right now. So it should be ready for Wednesday and everything should go as planned. But for now, the idea is Monday, Wednesday, kind of compensate for last
So it's going to be basically 2 episodes.
Yeah.
But we're just going to drop them one after the other.
Mm-hmm.
And that's just, because should we name it 90 and 91 or no?
It's not another episode though,
Yes.
right? It's just a part 2.
It doesn't really matter at the end of the day.
So yeah, this is going to be called kind of the history of physics, the scientific revolution. Because all these individuals were, this is old. We're talking 1500s today, ladies and gentlemen. So these individuals, I mean, you've already read the title, but these individuals all participated in the scientific renaissance, in the time period where science was really being birthed, basically. People were really starting to question things instead of just taking it the way that it was. And even though the idea of science was present centuries ago, the actual theory, the actual practice of actually performing the scientific method was mainly started in this era. So we're going to be talking about scientists that were very closely related to that era.
Before we get into it, we have a quick news session. Very quick. Here we go. Boom. Almost at 20,000 followers on Spotify. We're currently at 19,800.
Wow, that's really close.
So very close.
So 20,000 by the new year, baby. That's going to be crazy.
Yep.
That's going to be crazy.
It should be within the next week easily based on past trends. Also, YouTube, we're at 2,120 subscribers. If you're listening to this on Spotify, just go on YouTube and hit that subscribe button. And make sure to like the video. Also, leave a comment. We will get to that in a second. In terms of downloads, we are sitting at 338,000 downloads in total.
500 by New Year. No, that would have been cool, but no.
So thank you so much to everybody for listening to the podcast and downloading the podcast.
As always.
Let us know if you have any suggestions. We do get some suggestions, some of which we don't know anything about.
Yeah.
So,
yeah.
you know, feel free to ask us to talk about anything, but just know like some topics are just way beyond what we know. And even if we did research on them, it's kind of like we're just talking about things that we don't know.
Mm-hmm.
So maybe we'd rather not make an episode about that. But if it's something that's like that we've seen before and haven't talked about, then yeah, for sure we'll make an episode about that.
Also, if you want to check out our Instagram at math.physics.podcast, we're kind of, I don't know if we're active, but we've been starting to, we always say this, we do lives now. We still do lives. More of you are coming on, which is great to see. So if you want to, interact with us, talk to us, like we literally just get people on. Like if anyone wants to have a conversation with us, they can just join the live and that just happens. So we're totally okay with that. If anyone wants to hop into at math.physics.podcast, we love talking to you guys. Any input, any suggestions, any questions that we can answer.
You know what we can do actually? I just thought of this. Like on our most recent Instagram live, I think we got like a max of like 20 live viewers. And so however long it takes, when we get to 100 live viewers, we will do a merch giveaway. We'll do that. So make sure to come join us. Watch our lives when we do them like once a month.
Yeah, sounds fair.
Unannounced.
No, on an average, probably once a month. But like we're trying to concentrate it more, especially now because winter break is coming up. Yeah, we're definitely going to be hopping on that. So if you want to come join us, it's not very scheduled. If we do have one scheduled, it's definitely going to be available on like the Instagram story and like we're going to be posting something. Mm-hmm. But mostly it's just we just spontaneously, hey, let's just go live. Yeah. So yeah, just come join us if you can. Okay.
Comment of the week?
Oh, yes. Why would you comment on one of the YouTube videos? God, Why would you comment on one of the YouTube videos? And the answer is the comment of the week. So every week we pick a comment from the YouTube comment. And this week we have, Sergio. We've had,
have we?
This is a famous listener of ours, Sergio Perez. And they say, hello, guys. Today's Spotify released its 2021 Wrapped, and you're my favorite podcast with a total of 1,500 minutes listening. Wow! Thank you so much for very good times and learning that you've given to me. Yeah. So thank you, Sergio, for that wonderful comment, and thank you to everyone who continues to listen.
And something that's awesome about Spotify Wrapped is that we had, I think one of like the slides that they gave us was that I think it was like 4,800 people have listened to our podcast more than any other podcast. So that's cool. That's really cool.
That's really cool.
Yeah.
That's really cool. That's that's basically 1/5. That's not bad.
It's not bad.
A good 20%. 20%.
That's bad. Let's get into the podcast. I love preambles. So let's give a little preamble to, the people and the times that we're going to talk about in this episode. So the 1400s, we're going to start off with Nicolaus Copernicus. He was born in 1473. And it's so fun to study astronomy and physics and to actually see the events and how they played out and how one thing was discovered, one thing was postulated, and that led to somebody else thinking of something else. And then all these ideas come together into one model. And then later we realize that that model isn't so good.
Usually that model comes quite a little bit later, though. Like the cumulative model.
There's always a cumulative model.
I guess because they're always building off of their previous. Yeah, I guess so.
But what I'm saying is that you have this set idea of how some things work based on either delusion or some observation that you made. It must work.
It would be like incompetence almost, because half those people don't even want to know. It's not even in their mindset to have these questions.
Who's they?
No, I'm just talking about the people, because you're kind of setting the tone, right? So I'm just saying like the people in this era. Are not.
I'm talking about the scientists.
Well, the people, the generalized people aren't even thinking about this.
Yeah,
and the scientists out of there are just general people who think.
Yeah, and that's also an issue though, which slows down scientific advancement. Is that somebody makes like a genuine observation and goes, "Hey, like this is how it works because I saw it happen. And then people go, no, that's impossible because I don't think that's how it works. And then, most people who aren't scientists and they just farm or whatever you do in the 1400s, they don't really care. Well, they care in the sense that it's like, oh, I'm religious, so in the heavens, everything is predestined and God has done everything, and so that's what they believe in. Yeah. And then as soon as some scientist comes around and he's like, no, that's not how it is.
Challenges your views.
Exactly. You go, no, this guy's not right. That's ridiculous. The heavens are perfect and that's just how it works. But actually, you're just like, that collective is just slowing down the process of figuring out what is actually happening.
I mean, at that time, there were literal scientists, we can say scientists, I guess. There were scientists that, discovered certain things and that went against the church's views or that went against the populace's views. They got crucified.
Yeah.
Man just died.
Yeah.
Like got killed.
Yeah, which is
so I'm just saying, like, people literally got killed for having a different opinion.
It's so ridiculous.
Or not even opinion, like a literal... it's not even an opinion, it's an observation that was made or something that leads to actual fact. But no, it challenges my belief that is based on my father's belief, that is based on their father's belief. So I'm going to believe that, and like that was just the whole time period at that time. So it's definitely a little bit interesting to see how these people thought, because it's very, very, very different than today.
The most obvious thing that you could think as an ancient person is that where we're living right now is the center of it all. Because you're living on this terrain and there's a sky, and then, you can dig for pretty far down, but it doesn't seem as though it ends, right? So it seems as though you're living on this plane of existence, and then there's some stuff above you. You don't know how far it goes. You don't know how far the earth goes downwards, and you don't know how far it extends horizontally. So it's kind of intuitive to be like, well, I guess this is life. This is the universe. Where I'm living is like the middle of it. Mm-hmm. You'd have no reason to think not to. It's not like you look in the sky and you see other planets with other people living on them. It's just like we're the only people here, and so I guess this is the middle. And whoever put us here is like they put us here on purpose, and so this is the center of it all.
Yeah, because I guess when there's nothing, the only meaning to life is, well, because there's no science, there's no, okay, why did this happen? There's no actual reason. So the only meaning to life is, well, your own made up meaning, right?
But
which
also,
it all started.
Like, that way of thinking also doesn't make sense in its own right, because I feel like, hypothetically, if I was alive in the year 0, and I would think, like, if this is the middle of the universe, like, how far can I walk that way? You know what I mean? Until it's not considered the middle anymore. Like, how far can you go? And so if I can go...
People probably tried that and died on the way.
Yeah, I know. But if I walk really, really far for a month, am I still in the middle?
I mean, and on the grand scale of things.
Well, like, you don't know that.
Yeah, you don't even know that. You don't even know that.
Exactly.
Because you can just see these planets that are like far from you, and they're just like, okay, you just know that this thing is revolving around you, of course, because you're so important.
So the ideas back in the day was that the stars and space is unchanging. Everything is perfect. You see these wandering stars, which is actually, I think, like the Latin meaning behind planet or something, Latin or Greek. These wandering stars were categorized as these objects that like rotate around the Earth because we see them periodically. Even though they don't, from our perspective, they don't do perfect circles around the Earth. People just kind of ignored that, and they said, yeah, like everything that changes in the sky revolves around the Earth. And so the ideas back in the day was that you had the moon, you had the sun, and you had some planets. Of course, they didn't know every single planet that we know now.
Well, they didn't even really know at that time about, and they only really knew about the moon and the sun. And then they were just like, yeah, but planets, like the only idea of planets that they had was like the real.
No, they knew planets.
But
Like, I'm talking Copernicus's time.
I guess. But like
No,
how good of a, because telescopes weren't really.
They knew about Venus, they knew about Mercury, they knew about Mars. I don't know if they knew
but
anything
they didn't know
beyond
that. Was the discovery already made that the planets don't emit their own light at this time?
I don't know. I think it was maybe thought of, but I don't know if
because how would they determine?
I don't know
if
they can confirm.
Because otherwise they would just think it's a star. Because I know a big.
No, they know it's a planet because they see it moving across the background of the sky.
I guess you can see that it's moving, so you think that it's something that's a star, but it's still giving out the same light, which might, I don't know.
They didn't have spectroscopes.
Yeah, no, of course,
like,
but I'm saying at that time, if they knew that planets also emitted, or not emitted, but reflected the sun's light and not emitted their own.
I don't think before the telescope you would be able to confirm.
Yeah.
You'd be able to
theorize maybe.
Yeah, but not confirm.
Yeah, I guess so.
But yeah, so their ideas were that there's the moon and then there's the moon and then the sun, which both revolved around the earth. And then beyond the sun, there were planets which moved in. This is actually a really interesting thing to think about because, like, to us it makes zero sense, but it's kind of a what they thought was that around the earth, I guess, yeah, this is definitely way beyond the flat earth times. They definitely knew the earth was round.
Yeah, flatter. I mean, Eratosthenes basically confirmed the circumference of the earth.
So what they thought was that there were these invisible fixed spheres around the earth, concentric spheres that would just, increase in radius, and then the planets and the sun and the moon would be bound to these fixed invisible spheres, and they would just rotate around in circles. And this gave order to the universe. It was like, yes, the earth is a sphere, and then you have these things rotating around the sphere in perfect spherical orbits, and nothing disturbed each other's orbits. You know what I mean? Because they're all on separate planes, on separate distances. And so everything would just be perfect. Everything would just revolve around these concentric spheres. And that's just how the universe worked. That's what the Catholic Church believed in. It made perfect sense because the universe is just this perfect geometrical creation of God, and the earth is in the middle of it because why wouldn't it be?
Because we're life.
Exactly.
We're life.
Why wouldn't it be?
Mm-hmm.
Now, here comes Copernicus. And Copernicus, he wasn't the first one to state this, but he was inspired. He was an astronomer, a polymath. Of course, back in the day, there weren't really scientists that were in just one field that we know as like physics today. There wasn't somebody who was just an astronomer. Back in the day, people were astronomers, mathematicians, physicists,
basically all
writers.
All of these individuals were polymaths, basically.
Philosophers, writers, artists, poets. Like, they were just everything at the same time because everything was just mixed in together, right? If you studied math, you were studying geometry. You wanted to explore the geometry of the universe.
Astronomy usually followed from geometry. Like, usually some sort of astronomy, a lot of these individuals contributed to. In some sense, some of them were observing. In some sense, some just built some things. Yeah. And, all of them because they just understood the way that geometry worked. And hey, if something is really far, like the light rays are basically parallel to any lens or anything that's incoming. So that's actually very important because parallel light rays hold quite significant properties with lenses. So like all these very interesting, summaries almost from these understandings of geometrical objects they could make from astronomical objects, basically.
So what I described earlier is a geocentric model of the universe. Geo because the earth, and centric because the middle. So Copernicus is famous for his heliocentric model. He was
Helio because of the sun.
Yeah, he was the first like famous person to really say out loud and yell it from the rooftops that the sun was in the middle of the universe and the earth went around the sun.
Wow.
He actually got this idea from like an older like Greek philosopher who said it. Obviously no one believed him at the time. And so Copernicus said, and he's like, you know what, I've made some observations and this just makes a lot of sense. Although this breakthrough idea is supported by, or I guess this idea supports later discoveries. But, you know, one person can't do all the work. And so he believed in the heliocentric model. He's like, yes, obviously, well, not obviously, but I believe that the earth goes around the sun and the earth rotates around itself once a day. That's how we get day and night. And then it goes around the sun. That's how we get seasons. And also, this explains the motion of some other planets in the sky. Because if you observe Venus, you never see Venus on the other side of where the sun is, right? Like if there's a sun, the earth, you'll never see Venus on the other side because that's just how it works, because Venus is closer to the sun than the earth. Now, in the geocentric model, people thought that all the planets were beyond the sun and orbited the earth. So all of a sudden, by just imagining that the sun is in the middle, you get these connections where it's like, yeah, that totally makes sense. Although there are still some flaws, because Copernicus still believed in circular orbits, which makes perfect sense.
I mean, at that time, how would you not? Why would
exactly.
you not believe in circular orbits?
Why would you not believe in circular orbits? You see the moon go around the earth, it looks like a circle. The earth goes around the sun at a certain period every year. Why wouldn't it be a circle? Now, unfortunately, it's not true. And it's somewhat, I don't know if it, I guess to an extent, it stumped his research, or what's the word? You know, like the ability to move on and find out other things.
Yeah, I understand your point.
Right?
Yeah.
Because if you just believe in something that's not true, then obviously you're going to find a lot of dead ends. You're going to be like, well, I can't explain this, nor this, nor this, and I have no idea why I can't explain it. And this is actually the case for scientists at any period in time. It's just there are some things you don't know, there are some things you believe in that just aren't true, and now you're trying to look for more answers. But the answers are just not in the direction that you're looking. And so you're just stuck there, and then you die one day, and then somebody else comes along and proposes something different. Now, the beauty in the heliocentric model, I believe, is that it literally just disrupted everybody's ideas of the entire universe. Like, imagine if I told you right now, I say, like, you believe in the universe, right?
Mm-hmm.
You believe in the universe is expanding and all this.
I do.
Now, what if I told you that our universe is actually part of a system of universes where there's like one big thing in the middle, and then there are many universes orbiting that big thing. And this was just a fact.
Mm-hmm.
And I told you that right out. I was like, I tell you, I have observations and data proving this. Now, all of a sudden, you have to continue your career, your scientific career, considering the consequences of this fact that you just think is unbelievable. Because your entire life, you just thought that the universe was like the only thing that was.
Mm-hmm.
And we just observe properties of objects that live within that universe. Now all of a sudden, I open up this window and it starts making connections to things that you couldn't explain before. And it starts to all make sense, and you're like, okay, this really does make sense. So you tell everybody, and all of a sudden the church assassinates you. There's the story of Galileo, which we will get to.
Oh no, but what happened to Copernicus in the end?
He just died.
No, but how? Just natural cause?
Yeah, just natural. He died at the age of 70. I think just natural. Caught like disease or something. I don't know. But he wasn't like assassinated because of his ideas.
No, because interestingly enough, I was reading this really cool thing on Giordano Bruno. And this is really interesting. He was an Italian astronomer, and he also supported the heliocentric model. And he was a little bit after Copernicus. And interestingly enough, I'm just reading right here. Basically, his unorthodox views angered church authorities who tried him for hearsay. He was burned at the stake.
Wow.
Was burned at the stake for having an opinion, or not even an opinion, but like I don't even know what was
you just found something and decided to tell people.
I guess people just did not like the fact that, again, it just challenged their beliefs, right? And that might be a nice transition into the artist who also changed the way that people thought about art. And this is Leonardo da Vinci. Believe it or not, Leonardo da Vinci was not only an artist, but also quite a lot of other things. He was an astronomer, he was an engineer, he was basically a polymath again. I mean, all these individuals at this time were all polymaths because of the variety of subjects that all entailed from like a couple of things that they were interested in, right? He was really interested in with like human anatomy. He was like interested in painting, stuff like that. He was interested in painting landscapes and stuff. But the real thing that he believed, and where it comes into science, is that he actually believed that science is, or like art, is a form of science, basically, right? And to quote himself, the sole imitator of all the manifest works of nature. And that's what how he describes art in terms of, or like what art is in terms of nature. And the way that he works in terms of just the history of physics, not necessarily, contributing directly, but all of his art in some way inspired something to be created a little bit later on in the future, right? So starting out, like, he never actually received any formal education. He never did anything after the age of 15. So like he wasn't really into anything crazy level, like high level. So it wasn't like a scientist going into that kind of stream already kind of thing. But his father, I believe, was actually interested in him pursuing the arts. So he continued going on, and he just got like a few ventures here and there until he was basically just painting some really cool things. And he also was making sculptures of a lot of these things. And after a lot of like what he was told to make, what he was told to draw, he would actually think, okay, how can this be modeled? So a famous thing that he actually came up with was a way to break down the parts of any object, to draw the individual parts and how they influence each other. So like the very first, like a basic engineering diagram was basically created by Da Vinci. And interestingly enough, Da Vinci isn't even his last name. His real name is Leonardo. And it's something else, like some long ass name, but it's basically Leonardo because his mom he was born out of wedlock, so he never had a family name, and he was born in the town of Vinci, so Leonardo da Vinci. So that's a famous thing, but that's something that I never knew. And a very famous thing about Leonardo da Vinci himself, obviously apart from his paintings, one of his paintings I can talk about that I really liked, The Last Supper. So really liked in the sense that it was funny because he actually did not use the correct paint on the correct mold, so it disintegrated very quickly, and it was not a very good painting. And actually, to date, about 20% of the actual painting is Da Vinci's. The rest is basically like restored over time because of all this kind of stuff.
Where is it? Is it in the Louvre?
It is in the original place. I don't know where the original place is. I forget.
I don't know.
It is in a museum. It is in a museum somewhere.
So it's in Italy.
Yes, it's probably, and it's most definitely in Italy. But again, I couldn't tell you exactly where. But I know that the original does exist. But hundreds of thousands of copies obviously have been made, and it's one of the most famous paintings ever, including with the Mona Lisa. The Mona Lisa is a really dope painting just because of that smile. Apparently, that smile conveys a lot. So, continuing on to like his actual like scientific endeavors, of another model that he actually was a companion to was the heliocentric model. He also kind of, because again, he was Copernicus's time as well. He was born in like 1452. And so very, very much in the time of this whole Renaissance period. And again, him with Copernicus, basically you can say kind of like began this whole idea of changing, what we think is reality to, hey, this is what we actually observe. So how about we just go with this, right? So he actually did, he did agree with the heliocentric model, and he was basically talking about if, he has a very famous quote. I'm going to kind of paraphrase it. He also, in this quote, he actually also talks about the planets reflecting the light. So I'm assuming actually maybe they did know at that time that the planets did reflect the light. He basically says a man on the moon would be able to see like the earth and the sun, not like the earth is in the center kind of thing. Like he would be able to see it in conjunction almost, like not that like the earth is in the center of the whole model. He said,
wouldn't that be true either way, even if the earth was in the middle?
Let me just read out the whole quote. How about that? So the part of the moon part is, and any one standing on the moon, when it and the sun are both beneath us, would see this, our earth, and the element of water upon it, just as we see the moon, and the earth would light as it lights us. I don't really get that.
I think they're talking about the sun.
I was just talking about the sun
lighting
reflecting.
the earth like the sun lights us on the moon.
Like on the moon.
Yeah.
Okay, so they're just talking about, again, so basically the sun. Oh, okay. You know what? That makes sense. Yeah, okay. So that basically kind of went ahead and agreed with the whole heliocentric model of
Wait, I don't get how that's heliocentric.
No, that actually does make sense though. I fully get that. Because what they're trying to say is if the sun lights up the earth and it also lights up the moon, that means like the earth and the moon are both like kind of just like planets or like around the sun.
Sure, but what if the earth is in the middle and then the sun and the moon are orbiting? Then there's still a configuration where you can see both at the same time. So
yeah, I don't know, man. This is just a famous quote.
Okay.
This is just a famous quote from Leonardo da Vinci. I guess you're right.
Yeah, I get it.
No, there's definitely an understanding that we might be missing here.
Yeah,
if anyone wants to entertain us, why not put it in the comments and let us know if we're misunderstanding this quote? Because it's a very interesting quote because, again, he does agree with a very, very controversial topic at that time, especially because remember Leonardo da Vinci has, even though his paintings got a lot of fame a little bit later. Leonardo da Vinci himself was still a very famous individual. Okay, so after the audio glitch, we're back. Had to set everything up again. So I believe I was talking about Leonardo da Vinci and his agreement with the heliocentric model. So he also in one of his notebooks that was actually preserved, he wrote hundreds of notebooks, right, where he sketched a lot of things, where he proposed a lot of things, a lot of ideas, and a lot of them were written. 31 were preserved. That's it. And in one of these notebooks, he wrote, "The sun does not move." Basically, which kind of entails, historians today to kind of believing that, okay, he believed in the heliocentric model.
It's funny because that's also not true.
Okay.
That's why it's funny.
I guess you're right. Because, in the grand scheme of things, you're right. The sun.
I'm pretty sure I read
definitely moves.
on Instagram that the galactic age of our sun is like 18 years. It went around the galaxy 18 times
Oh, that way?
since it was born.
250 million is one orbit.
250? I thought it was 220.
Somewhere around there. I think it's
I mean,
I'm pretty sure it's. I might be
that's
wrong,
still,
but it's somewhere around there. I guess 30 million years is a long time. Is a long time. But yeah, sorry. 30 million years is a long time. But it's somewhere around in that range. So sun is definitely moving, but at that time, at least, he supported a model where the sun was in the center. Again, very, very controversial for its current time, right? Another really cool thing that definitely comes up with the exact practice of physics, because again, he was a scientist again in terms of art. Like he wasn't really a scientist in terms of direct science.
I mean, he was though, wasn't he, with astronomy
Well,
and
all with
engineering?
astronomy, he made like deductions. He didn't really make like, for example, a very famous thing with light. He made deductions of light, that there were 4 different types of light: diffused light, atmospheric light, like from the straight from the sun, reflected light, and then at that time it wasn't. No, but I mean, I guess refracted wasn't a word, but basically he defined it as light that goes through objects, that passes by objects. So he classified, again, he was more of a, I observe this, I'm going to make some really smart deductions.
Didn't he make things, like he made inventions?
Well, he sculpted things.
I thought he made inventions.
Not like a physical thing, though.
Oh.
No, not like a physical, I mean, like not physical objects, like his very famous helicopter that I want to get into.
He didn't make it? I thought he made it.
No. What? The technology was far from its time. From its time. So again, he was mainly credited again with the mind, because as I mentioned previously, this guy didn't do formal education. Like 15 math done. Like he was interested in it, but that's it. Right? Like he didn't actually continue. He didn't actually go forward with any of these scholarly, like these scholarly individuals did. Right? So he definitely is a little bit different, but his mind thought in the way that a scientist's mind does. You know, so he was a scientist, just not with the credentials. You know, so he still had the way of thinking, which I think is really powerful, because I think that's the whole premise of a scientist. A very famous quote from him, because at that time, a lot of scientists, quote unquote, would do things, would make things and say, oh, this happens and this is why it happens. Or they see things and it happens because this is why it happens. And that's not really a theory. That's not really an understanding. That's just saying, oh, it happens because I saw it happen. But that's not a reason. And a famous quote from him is, he who loves practice without theory is like a sailor with no rudder. I think that's really powerful, because I mean, it's very, very, very true. Like if you're in a body of water with your boat, you can see your boat in the body of water. You can maybe judge a few properties of that boat, but you can't take that boat anywhere.
Wait, is the rudder the thing that
Steers it.
Okay, yeah.
Yeah.
So you can still go.
What do you mean?
You can still go straight.
Okay, but like you can't, you know what I mean? The point of the quote is basically you don't really have an understanding of the boat.
Yeah, but you don't have
without-
direction.
You don't really, yeah, I guess so. Yeah, I guess you don't have direction is a nice way to put it. And he really strongly believed in this whole understanding of, you know, theory is important, even though he was still theoretical, because at the end of the day, like, he was trying to mimic all these real life objects. He was trying to put it in his work. He was trying to put it in his paintings and show what he could model, stuff like that. So he was still making deductions, just not as scientific, of course, as like a scientist, like a proper scientist of the day. So coming to maybe one of his most famous scientific, his most scientific contributions, the aerial screw, or basically the modern day helicopter. So he came up with this thing, with this idea, and just listen to this idea. Like, it's crazy. He was looking at maple seeds falling from a tree, right?
The ones that spin.
The ones that spin.
Maple seeds. I thought those were, I don't know the word in English, but it's like the leaves that are really like wavy, you know?
Yeah, they are like that.
No, those are pointy. Maple leaves are pointy.
Okay, I've read maple seed somewhere.
Okay.
I read maple seed somewhere. It was some kind of seed. It was a seed that spins when it falls. Anyways, point being that when the seed was falling, and when it falls, it spins, basically. It spins as it's falling. So he says, this is a quote, if the seed spins while it is falling, would it rise through the air if it was spun?
Oh, oh, that's kind of cool.
What a connection.
Whoa.
What a connection. What a connection. So he basically thought of like the modern day, well, helicopter, right?
Whoa.
Like the chopper, where you have your rotary blades pushing air down to lift you against the force of gravity. Now, at that time, there was no machinery, there was no engine, there was nothing really possible to lift against the force of gravity with power.
Were there hot air balloons?
Yes,
Okay.
yes. Hot air balloons were present. I believe it was invented by the Chinese.
Really?
And their original invention was straight up burning fire with a balloon that
Whoa.
just takes you up,
Whoa.
right? And that is still going
That's
up.
crazy.
That's
though.
still pretty cool.
Like imagine
to really
some-
discover
you
that.
just-
You're like, oh shit.
like you go to the town center. There's just a couple of guys
because the actual
like
science behind that is very powerful.
no, I know, but
like
I'm
what's
saying
actually happening to go up is
Yeah.
really, really strong with like the whole pressure differential and stuff like
what
that.
I'm saying is that imagine you're like just a normal day. You go to the town center and there's just dudes like filling this balloon and they just start flying and you're like, what is going
That would
on?
be very funny. That would be very, very
Like this has
hilarious.
never happened before and like people are just flying in the air now.
Yeah, no,
That's
it's
just a
definitely
thing.
a new thing. But so at that time, like flying, or not flying, but like going in the air wasn't unheard of. But doing it with like your own engine, like you're making
Yeah.
your own power instead of like
Yeah.
lighting something, or where you can actually have direction, was actually invented by him. And again, invented as in like a sketch. It wasn't, again, nothing was actually invented. It was simply a really detailed sketch of, again, I mean, not like I can describe it very well. Just look it up. just look at it. It's very famous. It's called the aerial screw, or you can just search for Da Vinci helicopter, and you'll see this very interesting sketch. That's basically this small rotor with this. Again, I can't.
Isn't
even
it like a
explain it. I can't
bike?
even really explain it.
There's like pedals on it and then it
No,
spins the thing.
it's just. I mean, the sketch is just this small thing with like this, like these fan-like screw, because that's what's called the aerial screw, because it's designed like a screw, and the idea is as it spins, it pushes the air down.
Oh, yeah.
But the only problem is we do not have nearly enough energy to make it spin fast enough to push enough air down at this time.
Mm-hmm.
So he had the idea. See, that's the thing with Da Vinci. And that's the thing with, I don't know, a lot of scientists, I get a lot of scientists also like kind of invented the things, but with Da Vinci in particular, he, you can say, was a scientist that was very, very well ahead of his time, in the sense that he had these ideas, he had these, like even with rivers, he was actually going deep into modeling rivers and how water flows through bodies. And the stuff that he was doing, you can't even think about doing in those days, that we can only do right now with like supercomputers, like, you know, calculating all these various trajectories and whatnot. So he came up with basically like simulations of stuff, like very, 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 very basic, of course. But in that day, you know, that was nowhere even thought of, nowhere, you can't even think about how much power you would need to supply. You don't even know how much power.
I mean, you
It's not
could
like-
you could probably calculate it.
Okay, probably. Actually, there
Yeah,
probably
you
is.
could
He
probably
probably
calculate.
didn't know
No.
himself, but there probably was a way to calculate the amount of power that would be required, of course. But
Wait,
all I'm-
was
all I'm-
energy
All I'm
was
saying,
no, actually, wait.
Conservation was
Conservation of energy was in Newton. So he wouldn't have even been able to calculate the amount of energy needed.
at that time.
Yeah, at the time.
At that time.
Wow.
Oh yeah, I
Yeah.
guess so. I mean, even Copernicus and all these scientists really were just like mainly observationalists.
Yeah.
Like they were just like, you know, they were making
Well, like
deductions.
mathematicans
the
also, like,
mathematicians, I
this is a
guess.
big
Yeah,
part.
mathematicians is power. See, that's what, you know what? That I think is what differentiates. Because again, a modern day physicist is impossible without being a mathematician in some way, of course. But if you bring up these old examples, like Leonardo da Vinci, for example, and you say he had no mathematical background, I think that's where you can split up the physicist or like the scientist from not. Because like that's where you also really see the difference. Because when you really like think of these and listen to these mathematical dudes, like in the 15th and 16th centuries, talking about, all these like you were talking about, like the sphere, like that's a very sophisticated way to think about a system, right? It's a very interesting way, I should say, not sophisticated. It's a very interesting, different way to think about a system that, in my opinion, only a mathematician would be able to think about. Because kind of like, I guess their brains in that time was also coded to think about geometry, because that was the only thing that they could think about.
Also, back in the day, before like modern notation was invented, math looked very differently. Very different.
Very different.
Yeah.
Very different.
So one quote from Copernicus that I like, and it's not even like a crazy quote, but here it is. He says, "Mathematics is written for mathematicians."
That's powerful.
Yeah, if you think about that.
English is written for, okay, well, but you know what I mean? Like, Spanish is written for, you know what I mean? Like, it's written for the person who understands that language is, I think, the meaning of that, right?
Somewhat, yeah. Like, it's in that same train of thought. But what I understood from that is, like, in school, we go to math class. We write down some symbols and stuff, and we do some theorems and a couple proofs. And it's like, people who don't do higher level math would just like, what do you look at that and you're like, oh, I have no clue what this, like, I see there's a letter A in this long string of characters, but like, I don't know what the message is behind this. I don't know what is trying to be proven. And even if I explain to you, like, oh, we're trying to prove this theorem because we can use it to conclude this and this about these specific examples. Like, it might even be the case that the application of the theorem is just like so beyond what a non-mathematician would even ever think about. Like, for example, like Stokes' theorem, Like, imagine going through a proof of Stokes' theorem in class and then explaining to somebody who has just done like high school math and explaining like the whole, like, not the proof itself, but maybe like why this is an important theorem. There's so many things that you need to know before that. And even to begin explaining it, you need to understand the language of mathematics itself to be able to absorb that information. And so when he says that mathematics is written for mathematicians, it's because the way this actually connects to something pretty interesting, which is like mathematical notation itself. It's so arbitrary. It's so random, Somebody, random, quote unquote, like, for example, Leibniz notation, like dy dx, like it's just a dy with a line and then dx. Like, it's so arbitrary, but to us it's like infinitesimally small change in the output over the infinitesimally small range in the domain that you're calculating this change in output. And you do that division and you get a ratio, and that ratio gives you the slope. That's the way that I interpret it. But if you were to just show some random person dy by dx, they say, well, it's just letters. And even with an understanding of addition, multiplication, and division, we could still explain it, but the core idea is really, it's behind the notation and it's in the actual concept itself.
And that is mainly mathematicians, I guess.
So yeah, well, I guess the goal of math is, one, to figure stuff out, but also, two, to write it as easily as possible and in the shortest amount of characters.
That's why it gets so complicated. Yeah. Because usually characters that you don't understand in math are just that. It's just characters that just represent some crazy. Yeah,
it represents something that would be too long to write out.
That's the only reason why they use it.
That's literally.
That's half of the.
That's like, literally everything.
Like a big chunk of math is, especially modern day math, is variables, right? And a big chunk of variables is just like substitution. And like when you see,
I mean,
this,
what do you mean by big chunk? I feel like
when I say
feel like
big chunk,
all
I
of
mean
it,
like, well, yeah, all of. I mean, like basically like all the equations.
like
and
even
everything.
numbers
But what I'm trying to
themselves are
say is,
notation.
like, for example, you see h over 2 pi everywhere. So you say, hey, let's make that another variable. That's literally how
I
you make
guess.
variables. You know, so if you
I was thinking more of like nabla, you know?
I mean, anything,
like-
even nabla would like you're
like
talking
a-
about.
Yeah, like the gradient
Gradient.
operator.
So so that can represent, that's an operator. So I guess that could also be thought about as an interesting variable that represents a lot of things.
I mean,
that can be understood by a mathematician.
I guess it's not by definition a variable.
I think
guess-
those are the ones that actually stump people. Like, again, at the end of the day, like just reading out what these are, you're like, oh, I can just plug in, But this is where you get stumped. You see this gradient and you're like, what is that? You know, because that's something that you simply don't understand because you don't have the, the knowledge, the background, the credentials to understand that.
Yeah, but I think
Hence the quote.
a really nice part about nabla, which I guess I can explain, it's a vector. I guess people treat it like a vector. I guess we can say that. People treat it like a vector. Here's how they treat it like a vector. Essentially,
you can think about it like a three-dimensional, or if you're doing,
it's n-dimensional.
N-dimensional vector.
So it's a list of the partial derivatives, just in order, based on how many dimensions you're in. So if you have a three-dimensional, like a function of 3 variables, then nabla is just going to be a list of.
This is only with a single variable output function, though. Like when it's what's that called? It's like
single valued
functions.
functions.
It's like when it all outputs to R, like
scalar valued functions.
Scalar valued functions.
Yeah, so you have 3 inputs and 1 output. So an example of this could be like position. You input your position in XYZ coordinates, and then the function tells you the temperature. So you have 3 inputs and 1 output. And so nabla is just a list of the partial derivative in X, partial derivative in Y, partial derivative in Z. And it's not really a vector because it's just a list of differential operators. But you treat it as a vector because you can dot product this with a vector. If you know how dot products work, you can cross product this with a vector. And you can just directly operate it onto a vector. So, for example, if you just operate it onto a function, I shouldn't say vector. If you operate onto a function, now all of a sudden you get a list of the first entry of the list is the actual first partial derivative of that function. And then the second entry is the actual, So the nabla itself is not the partial derivative. It's just the partial derivative operator that you need to operate on something to actually get a result. And so that's why I don't really know if you can call that a vector. But yeah.
You can think of it like a vector. Again, in the 1500s, if nabla was a thing, they would be thinking about it like
I think it was. Maybe not.
Calculus, bro. What are you saying?
Yeah.
Calculus wasn't invented.
Oh yeah.
So when nabla finally did become a thing, I mean, again, I don't really know their geometrical mindset if it was still based highly in geometry like that. But I'm saying if it was a thing in this day and age, they would, I think, 100% think about it like a vector.
But I think
because it literally represents like, oh, you go df dx in this way, you go df dy in that way, and then just continue. Like you can just think about it like a vector.
So first of all, I'm talking about nabla itself, not nabla operating on something.
Oh, you're talking about nabla itself.
Yeah.
Because nabla f is a vector.
Yeah.
Is what I was thinking.
Well, f evaluated.
Yeah, well, I mean, it's an x, y, z. But yeah, evaluated.
Like evaluated at a point is a vector.
Evaluated at a point.
So, anyways, the whole point of what I was saying connects back to notation, and it's that curl on its own is something separate from divergence. They have connections, obviously, right? They're connected in some way, but the thing is, but the people who came up with the notation could have gone in separate directions and called the curl of something defined it as its own piece of notation, and the divergence as its own piece of notation.
And not in terms of integrals kind of thing. Like its own. Like you're saying like its own
Sure.
operator.
Yeah.
Like you're saying, yeah. Well, even though there are
Why-
curl operators.
It's the language of the universe.